Okay, let's continue to the last section, not including the extra one, but yeah, that's the section 3. So last time in the previous clip we talked about how we can compute the confidence interval. Right. So that one is that one was the standard confidence interval with the formula x bar. The goal was to estimate. You use the x bar, you use the information from the sample to estimate mu, the actual population mu. We're trying to estimate. And in the previous case, we have like a nice scenario, a nice assumption that we know the sigma, that it is normal, and that whatever. Okay. But the key concept is that the result is going to be in the form x, not x, whatever point we estimate, right? Whatever value plus or minus some error. Okay. And that error will be different for other kind of problems. What kind of problems? If you recall, we have the x bar, we have also the proportion, a sample proportion p hat, and we can use that, of course, to estimate the population proportion p, and we can use the sample s standard deviation to estimate the population standard deviation sigma. And we can estimate all these 3 values. They are gonna have different formulas, but they have the same concept. You have that point, whatever you can compute, plus or minus some error, and you're gonna have a confidence level with some 1 minus alpha confidence level, confidence level. All right. So we need to get an error by some formula, and then we it is getting so low, and then we have to specify our confidence level. If it's 95, 90, 99, or whatever, that's gonna change the error. Okay, because either increase or decrease the size of the interval. So now let's take a look at what. Oh, let's take a look at how we compute the rest. Oh, by the way, in the first problem, if you may notice something weird, like we use this x bar, like we use the sample, and what else we use? We use sigma. We use these 2 parameters to estimate the population mean. Okay. You can see the problem is if we don't know the mean, then how can we know the sigma? Like, how do we get the sigma in the first place? Like that's maybe kind of weird. Like if the population is large, if you don't actually know, then how can we get sigma in the first place? And the answer is sometimes we don't. This is acting weird. Like the answer is we can't. We don't. Right? Sometimes we just estimate it. If you know this kind of problems, let's say we deal with people, and most of the problem about people, most of the statistics, people then have sigma between these small values, then we can use that sigma in your problem as well. Okay. Or if you know that this population follows some specific distribution, maybe binomial, hypergeometric, geometric, then that problem will give you a sigma also. So sometimes you get sigma, okay, not by measuring the whole population, but by some estimate or some math. But if you don't know sigma, if there is no way to get the sigma, then we have to go back and use the sigma from the sample. from our sample to estimate the population. And this one is gonna be more intuitive. But nevertheless, it's gonna be harder to use. Like this one is like the ideal case that okay, we can use this and compute and get one single nice value. Done. In general, it's not gonna be that easy. And you will see in a moment why. Now the problem is okay, we still attempt to find the confidence interval. For what? For the mean, the same thing. But now the sigma is unknown. And since we don't know sigma, then we have to compute the sample standard deviation as. And this is the usual formula that we have for the standard deviation, which the only difference is this denominator we have n-1 instead of n. This one is the concept of the degree of freedom, which we are not going to focus on this course. But if we compute all this the standard deviation from the sample, then we have to subtract the number of samples by 1. Anyway, once we have that S, then we can use that S to construct the confidence interval as before. So we have x bar at the same number, we have S that we just compute, we have n again from whatever. Now we have something new, we have t. Wait, what is t? What are you doing here? Like last time, what we have before we had okay, last time we have z, right? We have c because we know that the distribution is gonna be normal. It's gonna be the nice one. Here it's not nice because we don't know sigma depth, so we cannot construct the whole normal distribution. So we have to use a different distribution. T, which is called again, of course, it's T, so it's T distribution. How can we find that? We can find that from the T table. The full name of this is actually the student T distribution. Just known as just the T here. If we have n, we have s. Sorry, if we have n, if we have alpha, then we can use these two numbers to look up the table and get t. And once we get that t, then we can just put it there. Right. You multiply t, whatever you got, by s divided by square root of n, and now you get the interval. So let's go here. So the type of question is gonna have the same format. In textbook, you gonna see like a paragraph instead. Sorry, in textbook you're gonna see a paragraph with all these variables replaced by a story. Like you don't see that okay, sample size 40 means x bar. You're gonna say something like, okay, let's say you bake cookies, you bake 20 cookies, and the average weight of those cookies is 0.5 grams or whatever. But here I'm just gonna use number because I'm a math person. So we have n, we have x bar, we have s. The difference between this problem and the previous one is that now we have a sample instead, not the population standard deviation. We have the sample standard deviation as here. Now we are again asked to find 95% confidence interval. So we can just use the formula. Before that, let's talk a bit about the curve. So we want we want this area, like we want to be 95% confidence, we want to be correct 95% of the time. We want the area to be like 0.95. That means the rest of the graph has to be 0.05. Since there are two parts, then that is split 0.025, 0.025 on each side. So we want to find the value of G, such that the area to the left is 0.25. The only difference is that this curve is not the normal distribution, it's the T, the student T distribution. So you have to use different F to get a different value. Nevertheless, once you get the value, then you put that value into this formula. Right, so that's 175 plus or minus T. Let me take a look. No, that doesn't work. Something is wrong with my shouldn't show this one. Sorry, let me take a look at. Oh, it works. You can take a look at. This is mess. Wow. Sorry. So we get some whatever number it is, and you put it here. You have S is 10, N is 40. So again, we gonna say that mu is in between some interval. Right, and again we have 95% confidence level. We are pretty confident it's gonna lie in this range. Just different problem, different requirements, but the same concept. So this is this is the usual case when you don't know the population standard deviation. Now we have we try to estimate something different, like we estimate the average. Right, that's done. Now we estimate the proportion instead. Right, and if you recall that we have the binomial theorem that says if the binomial distribution have a large value of n and the value of p is not too extreme, is not close to 0 and 1 with a very large n, then that curve, right, that discrete case will look close to the normal distribution with this parameter instead. Yeah. So if you use that fact, then we can get a confidence interval for this one, for this normal distribution, and that interval will give us this formula. So what is this formula? Again, we have p hat. We have p hat. Right, the value that we get from our experiment or our sample. We have the same z from the C table, but what we put here is different. Like before, we have sigma over square root of n, and then this one is still actually the same sigma over square root of n, but since this is we have different sigma now. Oh, sorry. If we put here sigma over square root of n, we still have the same sigma over square root of n, but we can get sigma from that formula, and that sigma turns out to be p times 1 minus p. So if you compute p hat to get these numbers, right, you have n the sample size, then you can look up the value for z alpha over 2, and you can put everything there to get the confidence interval for the proportion. So now let's get back to our balls, pokeballs, our balls here. So let's say we take a sample of 150 balls, okay, and let's do the simple proportion of p hat equal to pi 4. That means we get 150 balls, right? And 60 of those balls what we interested in. And 60 over 150 is pi 4, right? So from this sample, we see that the proportion is pi 4. What can we say about the actual proportion of the whole bag, the big bag, that might have thousands, 10,000, millions balls, right? So let's just use the formula here. The proportion is not going to be exactly pi 4, but we can say for sure with 95% confidence level that it's gonna be oh, let me my laptop is getting too slow. Minus p hat minus p hat over n. And p hat is 0.4. We have a 95% confidence interval, so we can get that 1.96 if we kind of memorize that. So what about inside the parentheses, p hat? Let's do 0.4. 1 minus p. Oh, p hat is the success rate. And 1 minus p is the failure rate. If the proportion of stuff we want to get is 0.4, then the proportion of stuff we don't want to get is 1 minus that number, which is 1 minus 0.4 divided by 150, and that's gonna eventually give us some number, and that's 0.4, that's 0.6 divided by 150. We can use calculator to compute that, but this one can be cancelled nicely. I think it gives you 0.04. That doesn't work again. Huh? I see. Here's me. Oh yeah, I was trying to get the number. Again, you can look at the slide. This is so infuriating. It doesn't work now. What's wrong with everything? Oh! Never mind. Okay, you know what happened? I have a camera set up here above my laptop, and one of the legs is on the shift key. So whatever I do here is always get modified by the shift, and I find nothing works. Alright, so now it doesn't have a shift key. Let's see if... Okay, it works normally now. let me get the number real quick. That number is, yeah, that number is we get the interval of 0.322 to 0.478. Okay, now that makes more sense. Now we can say for sure with 95% sure, 95% confidence that the actual proportion of the balls in the bag, no matter how many balls are there, we can say that the proportion should not be too different from this range. The proportion should be between 0.3 and 0.4. Can it be 0.5? Yes. Can it be 0.6? Yeah. Can it be 0.9? Yes. But that is gonna be like pretty low chance of like at most 5%. So that's a proportion. Oh, by the way, this is probably more useful. I mean, it's useful both the means and the proportion. But in terms of like if you study games, math, probability, you want to get this number, then you are gonna be faced most of the time with a question about proportion. Then the mean. And finally, let's end. Oh, not the end. Yeah. We have two more confidence interval. Now we have the interval for the variance sigma. We have S. We can compute the sample variance. We want to use that to estimate sigma. Yeah, but the problem is that sigma is harder to estimate because if you remember, it involves square root. It also involves means. You have to know means before you can compute the sigma. So that's harder, and you can see the formula here, right? That is more complicated. So we, but nevertheless, again we have to know what kind of distribution it is. We know that the distribution for the sigma is a chi-square distribution, and that's why we have to go to the chi-square table to look up for the values to put in. Now n is now the numerator. Before we have n, that we have the square root of n as denominator, but now n is up here instead. Now we have s, the sample sigma. So just again different formulas that can be used to estimate the actual sigma. Oh, and we're gonna study briefly about the chi-square distribution at the end of this class, of this course, not class. Yeah. And finally, we have confidence intervals for two population means, right? So sometimes we get a nice sample, like one set of data, and then we plot a graph, compute all the values, and then we notice that, oh, actually we have two bell curves. Right? What it means that we actually like mixed up two different sets of data. Wait, we may not mix them up, right? But we might not know in the first place that all these data are actually split into two data sets, like males or females, like, or experience before the data we collect before we perform an experiment, and the data we collect after we perform the experiment. Yeah. So if we have two different sets of data, then we can compare the mean. Right. If we just look at the graph, then we will see one nice continuous curve. Okay. But our goal is we want to determine the difference between these two curves. Right. If we can, if possible, then of course we want to split these two into two different curves. If we actually be able to go back to the data and maybe clean it up somehow and get two different set of data, Then if not, then we have to kind of like combine them together. And in that case, then we can compute the confidence interval for the difference between two data sets. Then this is what we have from the experiment or from the samples. We can compute that by use that as the reference point and plus or minus the error. And that error still looks familiar. We have the z here, we have the sigma, we have the n. But now since we have two sets of data, 1 and 2, then we have to compute these two separately. Again, just a matter of using different, of knowing which formula to use. But the actual job of using that itself is just doing math or using calculator. I'm just gonna skip that. So the kind of question is gonna give you the x1 bar, x2 bar, sigma 1, sigma 2, n1, n2. You just put all of them, bam, into this formula and get the same kind of answer, which is gonna be an interval. And as an extra, this is not directly related to what we are studying. It's kind of like a little bit more advanced, a little bit more math. But nevertheless, the idea behind this topic itself is very useful. And this is the channel. You can click on this link on the slide, and that will direct you to the channel. Well, I think I can put it as a card. But anyway, if you have time, then please go watch this clip. It's gonna take 10 minutes, and this has very nice animation of this topic. So the idea is, again, this is still the same line of thought, right? We know we can compute the x bar, but we don't know about the mu itself, the actual number itself. We can use that to kind of estimate the actual number. We know p, we can compute p hat, but use that to compute p. We know s, we want to use that to estimate or compute sigma. Now this for this clip, this is a different one. It's gonna be loosely related to the p, the proportion. But this is used in a different wording. This is used as a probability. Like we have a probability of something. We want to use that to estimate, like the actual probability. This channel says this better than I do, so please go watch it. Great channel. Oh, by the way, if you are interested in awesome math, then this channel has like so many nice animations on math with very nice explanation that goes back to the actual concepts behind the formulas. Not just teaching you how to get or how to compute the formula, but the idea behind that formula. So I think that's it. So I am going to have short homework. Not sure if it's gonna be uploaded at the same time as this clip. But anyway, so that's it for this week. See you next week.